This webcast discusses Worksheet 9A on conductors and insulators and on how to create charged objects. At the top of this worksheet, we have a depiction of an iron nail, which is neutral, and also a plastic rod, which is neutral. And we're asked to explain the arrangement of the electrically charged particles in these two objects. And so I'm going to just take them one at a time. When we look at the iron nail, iron is a metal and it is a conducting material. It's a conductor. Right now it is neutral and it has an equal number of protons and electrons. We're going to represent a proton with a plus sign and an electron with a negative sign. Of course, in drawing them as pluses and minuses on this nail, the way that I've done it, these are much larger than the actual subatomic particles. But by drawing an equal number of pluses and minuses, I'm representing the fact that this nail is neutral. The positive charge of its protons is balanced by the negative charge of its electrons. The protons are located in the nuclei near the centers of the atoms. And in something like a nail, which is a solid, the atoms are rigidly bonded to each other. In this case, since it's a metal, they're in a crystalline structure. The protons never move. So anytime I represent this nail, I'm going to show the plus signs evenly spaced along the length of the nail. In a conductor, the valence electrons in the atoms are freely mobile, and they're able to leave their atoms and migrate freely throughout the nail. But in a normal situation, like this one, the nail is not polarized, it's neutral, and so there is just an even distribution of charge throughout the nail. Therefore, I see those electrons just located in the spaces between the plus signs. So I have an alternating plus, minus, plus, minus. Okay. In the next drawing, we have the plastic rod, which is also neutral. Now, plastic is a type of material called an insulator, and an insulator is a material in which atoms hold on very tightly to their electrons. So in this case, the rod is neutral. It has an equal number of protons and electrons. The protons are located in the nuclei near the centers of the atoms, and those atoms are rigidly bonded together. The protons never move. But the difference between how we show the distribution of charges in the plastic insulating material and the iron conducting material is that for the insulator, for this plastic, we represent each atom by a circle. And the circle represents the electron cloud. Because the electrons are tightly tied to their atoms and are not allowed to move away from the atom, that circle represents the boundary where the electrons are located. And so we don't really show minus signs when we're showing an insulating material. We show the plus and inside the circle, and the circle represents the boundaries of the atoms. They represent where the electrons are moving around. In normal situations, like this, when the rod is not polarized, the electron cloud is symmetrical around the nucleus. So in other words, the plus sign is at the middle of that circle. Okay, let's look at the next question here. Here in question number 2, the nail and the rod are brought close to a negatively charged Van de Graaff generator. The nail and the rod never really touch this generator. A Van de Graaff generator is that sphere on a pole here in the middle of this figure. It's a machine that is able to generate a lot of negative charges, so almost an infinite amount of negative charge that just accumulates on this sphere. So that ball becomes a very strong negative charge. I'm going to discuss the metal nail first. So when you bring that metal nail close to, but not touching, the Van de Graaff generator, the electrons inside the metal nail are repelled by the strong negative charge of the Van de Graaff generator, because like charges repel. So the freely mobile electrons, they move away from the Van de Graaff generators. They're allowed to, move away from their atoms, and so they do. They move to the far right side of the nail as far away as they can get from that negative Van de Graaff generator. The change in the location of the charges is called polarization. So the metal nail has become strongly polarized by being close to this charged Van de Graaff generator. Overall, the nail is still neutral. It has not gained or lost electrons. It still has one electron for every proton. It's just that their positions have changed. So it now seems that the pointed end of the nail has more of a negative charge because a lot of electrons have gathered in that region. And it seems like the other end, the left-hand side of the nail, has more of a positive charge because a lot of electrons have left that region of the nail. But if you were to move this nail away from the Van de Graaff generator, it would go back to looking like it did in number 1. All of the charges would just be evenly distributed again. It would no longer be polarized. Okay, let's look at what happens to the plastic rod when you bring it close to the negative Van de Graaff generator. So the electron clouds inside this plastic rod are also repelled by this negative Van de Graaff generator. But because the plastic rod is an insulator, the electrons are constrained. They are not allowed to leave their atoms. And so the electron cloud shifts slightly. It moves as far away from the Van de Graaff generator as it can, but it's still inside the atom, so that's not a very big distance. Now, our way of representing this is not a perfect representation, but it gets the idea across. We show what originally were round circles that represented our atoms. I'm now changing to ellipses to give that idea that the electron cloud has shifted. And you'll notice that that ellipse, there's more volume in the ellipse to the left of the plus that represents the nuclei than before. So the ellipse is not centered on that plus sign. It shows it shifting away from the Van de Graaff generator. Now, this plastic rod has not gained or lost electrons. It is still neutral, and if you were to take it away from the Van de Graaff generator, it would return to looking like that plastic rod did in number 1. All of the atoms would, return to their circular shape with the electron cloud symmetrical around the nuclei. Let's consider number 3. Here you get to meet Mike Piepan. That's the little guy with the crew cut here. And he's holding a metal pie pan. He's using a wooden handle, which is an insulating handle. And on the left-hand side, Mike touches the metal pie pan to a negatively charged Van de Graaff generator. And when he does that, by touching the pan to the Van de Graaff generator, there's like a bridge created. Electrons are able to move between the Van de Graaff generator and the pan, and that's what they do. There are so many electrons on this Van de Graaff generator, it has a very negative charge, and charge always takes the opportunity to move from a more negative charged object to something that has less negative charge. And so electrons move into the pie pan, and they're moving by the process called conduction, because the two objects are touching. Now, at the same time, the pie pan has become strongly polarized by being so close to this Van de Graaff generator, and the freely mobile electrons are repelled by the negatively charged Van de Graaff generator, and so they migrate to the side that's further away from the Van de Graaff. And you'll notice that not only, so I've represented the atoms here with 7 plus signs, and notice they're kind of evenly distributed around the pan. So those protons don't move. The atoms are rigidly bonded, but the atoms can't, but the electrons can move. And so I have 7 blue minus signs. Those represent the original electrons that were in the pan, and I've also shown, I think, 6 red electrons. These are the excess electrons that the pan has gained because they moved in by conduction from the Van de Graaff generator. Okay, so that was the picture on the left. Then Mike pulls the pan away, and he moves far away from the Van de Graaff generator. So now the pan is no longer polarized, and so the electrons become evenly distributed throughout the pan. But there's more than one electron for every proton now. The pan now has a net negative charge because it has gained electrons from the Van de Graaff generator. Okay, then in step 4, Mike takes his negatively charged pie pan, that's the one that he created up in step 3, and he touches it to a neutral pie pan. So when the negatively charged pan touches the neutral pan, electrons move from the more negative one to the other one, and the electrons move until both pans have the same electric charge. The process that, by which the neutral pan is becoming charged is called conduction. It's because the two pans are touching. Now, in the picture on the left, the electrons have moved until both pans have the same charge, and there's a little bit of polarization here. So those excess electrons are kind of moving to the sides of the pan away from each other. When he pulls the two pans apart, the electrons return to being evenly distributed in both pans. Both pans now have the same negative charge. Okay. In number 5, Mike has 2 neutral pie pans, or initially neutral. The pie pans themselves are touching each other, but he brings the 2 pie pans that are touching each other close to a Van de Graaff generator, but it never touches the Van de Graaff generator. Okay, so these 2 pie pans, they become strongly polarized because they are close to a very charged object, the Van de Graaff generator. So the freely mobile electrons in those pans migrate to be as far away from the Van de Graaff generator as they can, because, right, like charges repel, the negative electrons are repelled by this very negative Van de Graaff generator. Since the 2 pie pans are touching, the mobile electrons are able to move across both pans. So some of the electrons from the pan on the left-hand side move into the pan on the right-hand side to be further away from the Van de Graaff generator. So then Mike quickly separates the pie plates, and then he takes them away from the Van de Graaff generator. Since the pans were separated, the electrons that had moved into the pan on the right aren't able now to return to the pan on the left. So that means the pan on the left has lost some of its electrons. It now has more protons than electrons, and so it has a net positive charge. The pan on the right has gained electrons, so now it has more electrons than protons, and it has a net negative charge. Because Mike has taken these pans away from the Van de Graaff generator, they're no longer polarized, and so the electrons return to being evenly distributed on the pans. Okay. In number 6, Mike brings a single pie pan that's initially neutral close to, but not touching, a negative Van de Graaff generator. And we've seen before that the metal pan becomes strongly polarized because it's close to this very charged object. And so its freely mobile electrons migrate to the right-hand side of the pan to be as far as possible from the Van de Graaff generator. While the pan is strongly polarized, and that's important, Mike is doing this while the pan is still polarized, he grounds the right-hand side of the pan. That's shown by this black wire leading from the right-hand side of the pie pan down to the ground. So at this moment, while the pan is polarized, that right-hand side of the pan seems to have a negative charge because there are a lot of electrons that have accumulated in that vicinity. Now overall, before he grounds it, the pie pan is still neutral, but that region seems to have a negative charge because of all the electrons hanging out there right now. And so, since that region seems to be very negative, when he touches this wire to the pan, electrons take the opportunity to move from this seemingly negative region down to ground. And so some electrons leak to the ground. Now, the pan is no longer neutral. It has actually lost electrons, and so it now has a net positive charge. So this two-step approach to causing a charge on an object is called induction. The first step that has to occur is polarization. And then while the object is polarized, you have to ground it. So that's the second step. Now in this case, Mike ended up with a pie pan that had a net positive charge. But in number 7, we're going to look at a similar situation. But here, after he polarizes the pan, he touches the wire, the grounding wire, to the left-hand side of the pan. Now that left-hand side of the pan seems to have a positive charge because electrons have left that region as they were repelled by the negative Van de Graaff generator. And so when the ground is connected to that seemingly positive region of the pan, electrons move from the ground into the pan. So by grounding this side of the pan, Mike is able to cause the pan to gain excess electrons, and so then it has a net negative charge. So again, the pan was charged by the process of induction, and induction takes 2 steps. First, the pan had to be polarized, and then while it was polarized, it had to be grounded.